Now, the standard topology, or rather the standard metric on finite dimensional real space, is usually taken to be the Euclidean metric. But from a purely topological point of view, it really doesn't matter which of the three metrics we take as the standard on finite dimensional real space, as they all generate the product topology, which in finite dimensions is coincides with the box topology. All right, so we're going to move back to infinite products for a moment and define a new metric. Let the points x and y with coordinates y sub alpha for some index set j, b points in the product space R j, then the metric that we'll name rho of xy is the supremum of the metric d alpha, x alpha, y alpha for alpha in j, where the distance between the components x alpha and y alpha is the minimum, or the smallest, of the difference, the absolute value of the difference of those components, or 1. That is, the metric d is the standard bounded metric. On real space, or the real line. Then this metric is called, the metric rho is called the uniform metric. On R superscript j. And the topology that it induces is called the uniform topology. All right, so we need to demonstrate that the uniform metric is in fact a metric. And once again, non-degeneracy and symmetry are trivial. We will demonstrate that rho satisfies the triangle inequality. Okay, so rho of xy is the supremum of the metrics, the distance between x and y in the metric d, which is the standard bounded metric on the real line. So this is d of x beta y beta, where d of x beta y beta is the supremum of d alpha y alpha. So as d is a metric, we have that d of x beta y beta is less than or equal to the sum of d of x beta z beta plus d of z beta y beta. Now, d of x beta y beta, or z beta rather, is less than or equal to the supremum of all the possible values for x beta and z beta, and so it is less than or equal to rho of xz. And similarly, the distance in the standard bounded metric between the components z beta and y beta is less than or equal to rho of zy. And so we have that rho of xy is less than or equal to the sum of rho of xz and rho of zy. So the triangle inequality does hold. The metric is indeed a metric called the uniform metric on R superscript j. So next, we'll show via theorem that the uniform topology is finer than the product topology and coarser than the box topology. And of course, all these topologies are on R superscript j. Okay, so let the set U be open in the product topology and let the point x be in the set U. Then the open set U is a product of sets U sub alpha, where U sub alpha is open in the real line for every index alpha, and U sub alpha is in fact equal to the real line for all but finitely many values of the index alpha. So let alpha 1 through alpha n be the indices for which U sub alpha is not the entire real line, then as each set is open in the real line, we have that for every alpha sub I, the point x, or the coordinate x sub alpha sub I, is in a basis element, which is the open balls in the standard bounded metric centered at that point with some radius epsilon sub I. And this is a subset of the open set U sub alpha I. So again, as each set U sub alpha is open in the real line, for these finitely many values of the indices for which the open set is distinct from the real line, for every point in that open set, there exists a basis element containing it, which is a subset of the given open set. So we will choose epsilon to be the smallest of these radiuses, or radii, and we'll let the point y be in the open ball in the uniform metric centered at x with radius epsilon, as we've just chosen it to be the smallest of the radii in the open balls in the standard bounded metric. Then the distance in the uniform metric between x and y is less than epsilon. So for those values of the indices alpha 1 through alpha n, we have that the distance in the standard bounded metric between the point or coordinate x sub alpha and y sub alpha is less than epsilon sub I for each of these values x alpha I. So the coordinate y alpha I is in the open ball in the standard bounded metric centered at x alpha I with radius epsilon sub I, and the coordinate y alpha is in the real line for all other values of alpha. And so we have that the point y is in the set U. And we have demonstrated that the open ball in the uniform metric centered at x with radius epsilon is a subset of the open set U. And so for every open set U in the product topology, and for every point x in the set U, there exists a basis element which is the open ball in the uniform metric centered at x with radius epsilon. And this basis element is in the uniform topology. Such that the point x is in this basis element, which is a subset of the given open set U. And so we have demonstrated, well, so the set U is open in the uniform topology. So we have demonstrated that every open set in the product topology is open in the uniform topology. And so the uniform topology is finer than the product topology. All right? So now, let the set U be open in the uniform topology. And let the point X be in the set U. Then there exists a basis element in the uniform topology, which is the open ball in the uniform metric centered at X with some radius epsilon, such that the point X is in this open ball, which is a subset of the given open set U. So let the set V be open interval of the form, the product of open intervals of the form, x sub alpha minus epsilon divided by 2 to x sub alpha plus epsilon divided by 2. Then this set V is a basis element in the box topology, containing the point X. So let the point Y be in this basis element V. Then the distance in the standard bounded metric from x sub alpha to y sub alpha is less than epsilon divided by 2 for every index alpha, so that rho, that is the distance between x and y in the uniform metric, is less than epsilon divided by 2, which is certainly less than epsilon. And so the point Y is in the open ball, in the Euclidean correction, in the uniform metric centered at X with radius epsilon. And we have demonstrated that the set V is a subset of this open ball, which is itself a subset of the given open set U. And so, for every open set U in the uniform topology, and for every point X in that open set U, there exists a basis element V in the box topology such that the point X is in this basis element V, which is a subset of the set U. And so the set U is open in the box topology. And so we have demonstrated that every open set in the uniform topology is open in the box topology. And so the box topology is finer than the uniform topology, or another way to say that is that the uniform topology is coarser than the box topology.